Good evening, everyone. So, I welcome you all to the Fluidization Engineering's problem solving session. This is week 12 session. So, the course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Guwahati. While this session is handled by myself, Ankara Karthika, a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So, uh, according to the course content, this is the last week. Like this is since this is a 12-week course, this session is the last session for problem solving session, and if possible we will be having one more session where we will be summarizing whatever we have seen till now, just to give you a brief idea which would be helpful in your exam preparation as well. So now we'll start. So the course layout is as follows. We have almost covered all the things required for the basic understanding of the fluidization engineering. So in week 1 to 2, we saw about the introduction to the phenomenon of fluidization, covering the aspects of advantages and disadvantages of fluidized beds and industrial applications of fluidized beds. I know this would be a repetitive of what for whoever is listening to the course from the start, but I'll keep it short today. But this is just for if people who are attending the session for the first time. So to give them an idea, we are just giving an intro on course layout because we are having a lot of time as well. So why not make use of it completely? So yeah, so in what is fluidization? By now we are all very much familiar with the concept of fluidization, wherein we pass the fluid, which can be a gas or liquid, inside the packed bed at a sufficiently higher velocity, so that the particles inside the bed starts to move and behave like a fluid. This phenomenon is known as fluidization. Why do we prefer fluidization? Because it has enhanced the um, mass transfer phenomena happening inside the bed when it is completely fluidized. Also, the heat transfer is completely uniform inside the bed, which makes it an advantage, whereas the packed beds are prone to hotspot formation. Therefore, it is preferable to use fluidized beds at such cases. And as we said, it enhances the mass transfer happening inside the bed. So why not always prefer fluidized beds than packed beds? Because it leads to the erosion of particles. If we are dealing with a highly costly material, it is very difficult to utilize such large amount of particles, and some portion of it getting wasted. So it is not preferable when we are dealing with the higher costly materials, and the material properties again play an important role. And industrial applications of fluidized beds, we have various applications in chemical engineering industries, like Fischer drop synthesis, polymerization, biomass gasification, and fluid catalytic cracking, and with major application on the oil industries. Fluidized beds are very much used in industries. You can see it in most of the industries which is dealing with the fluid particulate systems. So in week 3, we dealt with the characteristics of solids, classification of solids, and as we all know, not all the solids behave the same inside the fluidized bed. So depending on their properties, like density and their size, the performance of the bed is highly influenced by them. So gel dart, what he did is he classified the solids into 4 categories: gel dart A, gel dart B, gel dart C, and gel dart D. Where gel dart A particles, okay, we'll keep it gel dart C particles, which are the smallest of particles. And since they are smallest, they are very much cohesive in nature, and it is very difficult to fluidize such particles. Next comes the gel dart A particles, where gel dart A It is comparatively larger than gel duct C, but again smaller than gel duct B and D. But it is widely used in industries. For example, FCC catalyst comes under gel duct A because bubbling is not that much observed in gel duct A particles. Next comes the gel duct B particles, where bubbling is very much seen. But again, it is preferable to use gel duct B particles than gel duct D particles, because in gel duct D particles they are very larger particles, so it is very difficult to fluidize those particles, and those particles are used in spouting fluidized beds. So, and flow characteristics. Week 4 to 5 we dealt with flow pattern of fluidization system, flow pattern transition, flow pattern map, frictional pressure drop and its model to analyze solid movement, mixing and segregation and staging. So when we are passing the fluid inside the bed, as we mentioned, it is above certain velocity requirement. So does the fluidization phenomena remain the same irrespective of the velocity? No. With respect to the inlet velocity, the fluidization phenomena is different. For example, we can classify it into two types basically. One is when we are dealing with liquid fluidization, the bed does not lead to bubble formation, that is known as homogeneous or particulate fluidization. Class 2 is nothing but heterogeneous fluidization or aggressive or bubbling fluidization, which is mostly observed in gas solid fluidization. Because in this, when we pass the fluid inside the bed, initially bubbles start to form inside the bed. With increase in the velocity, the bubble starts to grow and slugging occurs. With further increase in velocity, the slugs grow in size and they almost reach the diameter of the vessel, and after that these bubbles in turn carry certain amount of solids with them, thus making it advantageous, not advantageous but enhances the solid movement inside the bed in terms of their wake, and once they reach the size of the vessel, the bubble starts bursting out, and because of that the solid particles are again thrown inside the bed, and it leads to vigorous fluidization known as turbulent fluidization, fast fluidization, and after a point the solids would be carried away from the bed, known as pneumatic conveying or pneumatic fluidized beds. So depending on the velocity, all these changes can be observed inside the fluidized beds. So in week 6 it was about gas distribution, types of gas distributors in small and large scale industries and design of distributor. So we know that not all like in industries, and when we are dealing in labs we use porous plate distributors, but the same cannot be used when we are dealing with industries. So distributor type and design is very much essential because it influences the pressure drop happening inside the bed, which again determines the pump characteristics required. So the pump characteristics fixes the operational cost of the plant. So again it is determining various other factors. So it is very much essential to know about the distributor system in the fluidized bed section. And week 7 we are dealing with, we dealt with bubbling fluidized beds. Again, in bubbling fluidized beds, by now we know that it is very important to study, and we must be in a position to predict what is happening inside the bubbling fluidized beds. So in terms of gas dispersion and gas interchange, mixing characteristics, because those bubbles only carry a certain amount of solids with them in the form of wake, and once they reach the surface of the bed, they again throw the solids inside the bed. So solid circulation in turn happens by using this, and depending on the binary, if two or more components are present, the fluid velocity range should be adjusted accordingly, such that we would be obtaining mixing or segregation, whatever is essential. And staging is nothing but when we are collecting the solid particles at each intervals of time, not each intervals in the bed. So the density, a certain group of particles with a certain density range should be collected. So for staging is used for that purpose. And week 8 it was about entrainment and elutriation from fluidized bed, which is nothing but the carryover of solids, mostly finer size particles, away from the bed, which is known as entrainment. and if we are dealing with collecting of certain range of density range of particles, it is known as elution. And week 9 it was about attrition mechanism, because since we are dealing with the solids and they are moving similar to that of a fluid, it is very much essential to understand what is happening and how solids are getting corroded or eroded. Therefore attrition mechanism is very much essential, because the solid can be fragmented or it can be broken into smaller fines, and there are so many phenomena, so many things happening behind the name of attrition of the solids. When we are dealing with the valuable materials, it is very much essential to understand what is happening a prior, so it would be beneficial during the process, so that we can avoid the loss of the material and so on. And week 10 to 11 it was about mass transfer phenomena happening inside the bed, because we have almost two phases in general. If we are categorizing the fluidized bed or analyzing the fluidized bed using model, we have a bubble phase and the emulsion phase. Emulsion phase is nothing but similar to that of the fluid fixed bed, where fluid and solid is present, and the bubble phase where no solid is present. So uh, it needs to be understood how the particles are traveling inside the bed, and particle to gas mass transfer, and like so many things happen behind it. And 2 and 3 phase systems and modeling, like it needs to be understood when we are focusing on the fluidized beds. And the last week it is about heat transfer phenomena. What are the heat transfer mechanism that is taking place inside the fluidized beds and the surfaces, and the modeling for the same, and the design for the fluidized bed reactor for physical operation. See, it is not only about physical operation, but also we are dealing with catalytic reactions and non-catalytic systems. So depending on the purpose, it is required to design the system accordingly. So unit operations, unit processes, all those we have dealt in the chemical engineering. So this particular phenomenon of fluidization, for designing the fluidized beds, we need to be having a complete understanding of the mechanisms that is happening inside the system. So this is the course layout. This we have covered almost everything in the content. So yeah, coming to the books and references, the basic one is Cooney and Levinspill's Fluidization Engineering. This almost gives us a complete picture of what is fluidized beds and what is happening inside that system. So it is very much recommended to for you guys to read the book. And next is the Gidaspo's multiphase flow and fluidization, continuum and kinetic theory description. As I have already told you before, the modeling of fluidized bed can be made under two categories. The fluid phase we would be using the continuum theory, but for the solid phase we can either go with continuum theory description or the Lagrangian, where in Lagrangian we track each individual particles, that is the complete mechanism, that is the true mechanism happening inside the system. Whereas for the purpose of for the sake of easing out the model, we go for the continuum theory description. In continuum theory description, it is nothing but the solids are assumed to behave as a continuum, and it is modeled according to kinetic theory of granular flow, which is similar to the kinetic theory of gases. So accordingly, kinetic theory description, continuum and kinetic theory description was formulated for the multiphase flow system, especially for the fluidization engineering. So third one is Gibbs-Lyra's fluidization dynamics, and fourth is Professor S K Majumder's hydrodynamics and transport processes of inverse bubbly flow. So this is the introduction for this. So we'll go to question 1. In question 1, it is asked that choose the correct option for heat transfer characteristics in a fluidized bed reactor. Options are, like, we need to match actually. So in the left hand side, 3 options are given: conduction, radiation and convection. Whereas in the right hand side, 3 options like particle gas or wall gas, and gas particle or gas wall, particle particle or particle wall. So option A, it is 1R, 2P, 3Q, or it is option B, 1P, 2R, 3Q. Or option C, it is 1R, 2P and 2Q and 3P. Or option D, it is 1R, 2P and 3R. 1 is Q. So this is the basic thing that is required for proceeding with the week 12 course. So what are the heat transfer characteristics inside the fluidized bed reactor? So if anyone can answer, it would be better. But again, I don't think anyone is there. So let us just take a moment to analyze what is happening, what the question is about, and what the answer is. So actually what happens is particle to particle and particle to wall, both are solids, conduction takes place, and gas to particle and gas to wall, convection takes place, and finally particle to gas or wall to gas, radiation takes place. So this we know that when two particles are interacting, if the transfer is from particle to particle, it is by means of conduction. Or else if gas is carrying the particles and by means of it is transferring some amount of heat, it is known as convection. Or else if the particle is giving out some heat to the gas, it is known as convection. So what are the options? Conduction is for particle particle or particle wall. Radiation is for particle gas or wall gas. Convection is for gas to particle or gas to wall. So it is R, P and Q. So I think it is option A, which is R, P and Q. Option B, it is wrong. Option C again is R, Q and P, which is wrong. So option D is wrong. Answer is option A, R, Q and P. So I hope you all understood. Conduction is between particle particle or particle wall. It is happening between the solids. And radiation is from particles to wall. Particles giving out some, particles to gas. Particles are giving out some heat to the gas. And if it is gas giving out heat, it is convection. By means of carrying over only, it transfers heat, right? So it is convection. If you want to take a minute to understand, we'll go to next question after that. We'll go to question 2. In question 2, which one of the following statements is true regarding heat transfer coefficient? Heat transfer coefficient increases with increasing thermal conductivity. Heat transfer coefficient increases with increasing density. Heat transfer coefficient increases with decreasing viscosity of the gas. All of the above. Um, this again is a straightforward theory question. So just give out proper reasoning, because reasoning only would help you in understanding what is right, and which the question is about which one of the statement is true. If one statement is true, other statements should be wrong, right? So just make sure what is wrong in that statement. If you are feeling the other statement is wrong, make sure to understand what is wrong and what is happening in that statement that is making it wrong. So we will discuss with when heat transfer coefficient increases, it is increasing with increasing the velocity of the gas, or increase in the thermal conductivity of the gas, increasing the density of the gas, and decreasing the viscosity of the gas. For example, if the thermal conductivity is increasing, heat transfer obviously increases, and if the density is increasing, the capacity to carry heat would be increased, and decreasing viscosity of the gas, again same thing. So therefore the answer is all of the above is the right answer. Option D is the right answer, all the above. We'll go to question 3. In question 3, it is asked that gas is passing at a gas velocity of 0.025 meter per second through a fixed speed of 3000 micrometer. Calculate the Prandtl number of gas. So we are given Cp of gas, which is 993 joules per kg Kelvin, and kg thermal conductivity of gas 0.026 watt per meter Kelvin, and density of gas, sorry, it is not gas. It is, I think, bed. 1.225 kg per meter cube, and mu viscosity of gas is 1.81 into 10 power minus 5 kg per meter second. So it is a very simple question. We need to calculate the Prandtl number, which we would have done in our BTech itself. So just find out the answer. Options are: first option A, it is 0.47, option B it is 0.10, option C it is 0.22, option D it is 0.69. So we will solve it. So we'll write the given data. And for the formula, we need to find Prandtl number. Prandtl number is again Cp mu by K. So Prandtl number is Cp mu by K. On substituting this, what we will be getting 993 into 1.81 into 10 power minus 5 divided by 0.026, which is equal to 0.6912. So option is, what are the option? Option D is the right answer. So answer is option D, 0.6912. So I hope this is clear. It is a very simple and straightforward question. So hope you all got the answer right. Now, if you want, just take a minute to analyze and we will discuss the next question. So now we'll go to question 4. In question 4, it is asked that the superficial gas velocity of gas at 0.05 meter per second passing through a fixed bed of particle size 3.5 mm. Calculate the Nusselt number of the particle, and data given is density of the gas, which is 1.23 kg per meter cube, and viscosity of the gas 1.83 into 10 power 5 10 power minus 5 kg per meter second, and Cp of gas, it is 993.0 joules per kg Kelvin, and thermal conductivity, it is 0.026 watt per meter Kelvin. So what we are asked? We are asked to calculate the Nusselt's number. So we are going to solve it. Are you guys willing to take a moment to solve that before I solve? I think that would be better. Uh, Again, this question is also a very straightforward question. So take just, it is similar to the Sherwood number problem that we solved in the last week. So similar to it, just understand it and we will discuss the answer. So we will solve this. Given data, we will write from the question. And in addition to it, we have U, which is 0.057 meter per second. 0.57 meter per second. So formula for Nusselt number. Nusselt number is equal to 2 plus 1.8 into Reynolds into 0.5 Prandtl into 0.33. So how do we calculate Reynolds? Is equal to rho, it is Reynolds particle actually. V dp by and what is Prandtl number? So we will substitute all these in that. Rho 1.23 into 0.057 rho V dp 3.5 mm, dp is 3.5 mm. Rho V dp by mu. Mu is 1.83 into 10 power minus 5. What is the answer for the Reynolds number? Did any one of you calculate it? It is 13.4090 and we need to find the Cp mu by K, that is Prandtl number 993.0 into 1.83 into 10 power minus 5 mu by K 0.026, which is equal to 993 into 1.83 divided by 0.026. It is 0.6989. So on substituting it into that, we will be getting Nusselt is equal to 2 plus 1.8 into Reynolds is 13.41 power 0.5 So which is again we need to do the calculation. It is what are we getting now? Can anyone say the answer? 13.41 to the power of 0.5 into 0.6989 to the power of 0.33. We are getting 2 plus 1.8 into 3.2537. So what we need to do, 1.8, we are getting 7.85 or 86. We'll see what are the options given. Yeah, 7.86 is the right answer. So how did we find out Nusselt's number? Nusselt's number is similar to the calculation we did for Sherwood number. Nusselt number is equal to 2 plus 1.8 into Reynolds power 0.5 and Schmidt power 0.3. Here Reynolds number is particle Reynolds number. So we are using rho into V into dP by mu. Whereas for Prandtl number we are using, rho V 2 plus 1.8 into Reynolds power 0.5 into Prandtl power 0.3. So there Prandtl number we are using Cp mu by K. So all the unknowns are given, values are given in the question. So it is straightforward substitution. So by this method we are obtaining the Nusselt number as 7.86. If you have any questions, please ask, or else we will move to the next question. So we'll go to question 5. In question 5, it is asked that choose the correct expression for the Nusselt's number. So since we did the calculation for the Nusselt's number only now, we would be able to calculate it. Choose the correct expression for Nusselt number. Nusselt number is equal to H into Kg in Hp into Kg into dP, or Nusselt's number is equal to Hp into dP by Kg. Option C, it is Kg dP by Hp, or option D, none of the above. So identify which one of it is the Nusselt's number. So I'll give you guys a hint. Since we are dealing with the heat transfer coefficient, so that term would be coming on the priority basis. So with this clue you would be able to identify the answer. So the question is about identifying the correct expression for the Nusselt's number of the particles. So it is particle Nusselt's number. So what would be the expression? So Nusselt's number here is used for heat transfer coefficient calculation. So that would come on a priority basis. That is the hint over here. And by now you can do it. So since we are dealing with the heat transfer coefficient, that should come in the top, that is numerator. So option C is left out from this. So option A or option D. So since we are dealing with H and Nusselt's number is a dimensionless number, on the bottom we need another one strong coefficient, so which is K. So H and K together, if it comes, it won't become dimensionless. So answer is option B, H dP by K. HP dP by kg. So answer is option B, Nusselt's is equal to HP dP by kg. So one of the hint in solving out few or identifying few problems is finding out the correct expression for dimensionless number. You can solve using dimensionless approach by sorting out the dimensions of all those things, or else think logically. Since Nusselt's number is dealing with heat transfer coefficient, that would come in the coefficient, that would come in the top, because if you see uh, here HP is coming at the bottom, it would not be the case, whereas in both of them HP is coming at the top. So yeah, either one of them is the answer. If we make dimensionless, option B is the right answer, HP dP by kg. But again, it is a simple dimensionless number, so you can always remember it. But in the worst case, you can go with the other approach too. Now we'll go to question 6. In question 6, it is asked that which is the correct expression for interfacial bubble area? A is equal to 6 into epsilon g by dB. Option B, it is A is equal to 6 into 1 minus epsilon g by dB. Option C, it is 6 into 1 minus epsilon g power 0.5 by dB. Option D, it is none of the above. So identify the right answer. Answer is option A, that is 6 into epsilon g by dB is the right answer. Where here we are using the formula to calculate the interfacial bubble area, that is A. So small bubbles will have more surface area, that is interfacial area. So we can relate it using the inverse approach. A is equal to 6 into epsilon g by dB. Small bubbles have increased surface area. So we'll go to question 7. In question 7, it is asked that in a gas liquid multiphase flow system at steady state, the liquid holdup is approximately 0.72. The observed average bubble size is 3 mm. Determine the specific interfacial area. Option A, it is 560 meter square per meter cube. Option B, it is 440 meter square per meter cube. Option C, it is 770 meter square by meter cube. Option D, it is 190 meter square by meter cube. So it is asked that read the question properly. In a gas liquid multiphase flow system, we are having gas and liquid. Liquid holdup is 0.72 and the observed bubble size is 3 mm. So what is the specific interfacial area? We need to calculate A. This is similar to what we have done in the past problem, that is a previous problem. So you would be able to find out the answer very quickly. So try to get the answer. It is a very straightforward problem. So you must be able to get the answer. If not, there is no if not, first of all. You can do it. We will discuss the answer in a minute. So in the question it is given that okay, we'll write the formula first. Based on this we are having to. So in the question, liquid holdup is given. So what is it? It is liquid holdup is 0.72. 0.72. So what is the gas holdup? It is 1 minus this. So 1 minus 0.72 is the gas holdup, which is nothing but 0.28. So we are going to calculate the interfacial surface area. So which is and also dB is given. dB is given as, what is the value given? It is 0.72 3 mm. 3 mm. 3 mm. So answer is 6 into 0.28 divided by 0.003. So it is 2 by 0.003 into 0.28. So it is 0.56 by 0.001, which is nothing but 560 meter square by meter cube. So this is answer is option option A is the right answer. 560 meter square by meter cube is the right answer. So how did we find out? We use the formula 6 into epsilon square, epsilon G by dB. Here the thing to be noted is epsilon G, that is gas holdup, is given in the interfacial surface area, bubble interfacial area formula. So in order to find out epsilon G, we are given the liquid holdup, which is epsilon L. So epsilon L is 0.72. So epsilon G is 1 minus epsilon L, which is 0.28. So diameter of the bubble is given as 3 mm. So after that it is a direct substitution in the formula, where the formula is A is equal to 6 into epsilon G by dB. So we know 6 epsilon G is 0.28 and dB is 0.003 meter. So we are putting it out everything and we are getting 560 meter square per meter cube, which is nothing but the option A. Option A is therefore is the right answer. So that is for the question 7. So I hope you are very clear with this. If there is any doubt, please let me know, or else we will take a small break and we will resume the session after 5 minutes. So we'll resume the session. We'll go to question 8. In question 8, it is asked that which of the following is the correct statement. Smaller bubbles have low rising velocity. Systems with larger bubbles have low gas holdup. Both option A and B are right. Option D, none of the above. So actually, if you are thinking which of the following statement is the right, smaller bubbles have low rising velocity. That is true. And how to say, system with smaller bubbles have low rising velocity, and also they have more gas holdup. As the bubble diameter decreases, the gas holdup is more. So the vice versa is again true. As the bubble diameter is large, the gas holdup is low. I hope you are getting my point. So what I am trying to say is, for the smaller bubbles we have low rising velocity, and for the smaller bubbles we have higher gas holdup. So inverse case is again true, which is that for the larger bubbles we have low gas holdup. So both options A and B are right. So I hope it is clear. If you have any doubts, please you can always ask. And question 9, in question 9 it is asked that choose the correct expression for Thiele modulus. Option A, it is phi is equal to dp by 6 into kr double dash into as by di. Okay. Or option B, it is dp by 6 kr double dash as by di to the power of 1 by 2. And option C, it is pi dp square by 6 kr double dash as by di power 1 by 2. And option D, it is none of the above. So we all know the answer to this. So before that, what is Thiele modulus or Thiele modulus, whatever you pronounce, what is Thiele modulus? So actually it is used for in catalytic, reaction rate. So it is nothing but it is the ratio of intrinsic reaction rate to the mass transfer rate in catalytic particle. So so it is used when we are dealing with the reaction engineering. So it is nothing but the surface reaction rate and the diffusion rate, or like simple terms. So it is nothing but the ratio of intrinsic reaction rate and the mass transfer rate in catalytic particles. So it is dp by 6 into kr double dash into as di by 1 by 2. Option B is the right answer. Now we'll go to question 10. In question 10, it is asked that the solids hold up in a slurry bubble column is 0.2. The slurry was prepared in the water with viscosity 8.9 into 10 power minus 4 Pascal second. Determine the viscosity of the slurry. Option A, it is 1.76 into 10 power minus 3 Pascal second. Option B, it is 1.56 into 10 power minus 2 Pascal second. Option C, it is 0.86 into 10 power minus 3 Pascal second. Or option D, it is 4.26 into 10 power minus 3 Pascal second. So, since I'll give you guys a minute time. In that minute, just at least find out the formula. If so, we can substitute the numeric values in that formula and give the answer. For that, first you need to identify which formula we need to be using to find the viscosity of the slurry when we know the solids hold up in a slurry bubble column and the water viscosity is known. So the formula should be relating the solids hold up and the liquid viscosity. So we'll solve this. Right now we are in question 10. So question 10 solution. So first we'll write given. What are we given? We are given viscosity of the liquid and the gas holdup. Remember guys, gas holdup is 0.2. So we are given epsilon and we are given mu. This is mu slurry, sorry, mu liquid. So epsilon s is given, which is nothing but 0.2. So we are asked to find the viscosity of the slurry. So what is the formula for that? Did any of you find out? Actually it is given in the lecture itself. So it is quite easy to find it. However, I am writing the formula again. It is mu L into 1 plus 2.5 epsilon s plus 10.05 epsilon s square, and again plus 2.73 into 10 power minus 3 into exponential of 16.6 epsilon s. Okay, it is not b. So now we need to substitute everything in this. Mu L is 8.90 into 1 plus 2.5 into 0.2 plus 10.05 into 0.2 square plus 2.73 into 10 power minus 3 into exponential of 16.6 into 0.2. So can anyone give the what answer you people are getting, or however I'll calculate, but it is always better to take a pen and paper when we are dealing with the sample problems, so that you can solve your doubts then and there. So it is, if you have any doubts you can always ask. 16.6 into 0.2, which is 3.32, and exponential of this value well, it is 27.66, which is the exponential value. Okay, I think I left out so many factors. Okay, 8.90 into 1 plus 2.5 into 0.2, it is 2 into 550, 0.5 plus 10 point, clear, where is clear, 10.05 into 0.2 into 0.2, 0.402, 0.402 plus 0.00273 into 27.66. So answer is 0.0273 into we are getting it as plus 1 plus 0.902. We are getting 8.90 into 1.9775. So 1 into 8.90, we are getting 17.5998 is equal to 17.5998, which is equal to 17.6 Pascal second. We'll see what the options are given. It is actually 10 power minus 3. Actually, I left out into 10 power minus 4 here, into 10 power minus 4. So again here that would come actually. Here it would come. Again here it would come. Is equal to 1.76 into 10 power minus 3 Pascal second is the right answer. So answer is option A, 1.76 into 10 power minus 3 Pascal second is the right answer. So what have we done in this particular problem? We are given the solid hold up, which is 0.2, and the liquid velocity, which is 8.90 into 10 power minus 3 Pascal second. So we are asked to calculate the viscosity, slurry viscosity. For slurry viscosity, we are using the given formula where mu slurry is equal to mu L into 1.1 plus 2.5 into epsilon s plus 10.05 into epsilon s square plus 2.73 into 10 power minus 3 exponential of 16.6 into epsilon s. So we know all the values because this formula is a very simple problem, in the sense we are having only two variables, which is solid hold up epsilon s and the liquid viscosity, that is a pure liquid viscosity, which is nothing but water here. So on substituting all these values in the particular formula, we are getting the answer is 1.76 into 10 power minus 3 Pascal second. So formula is this. So that's all for this question. Now we'll go to question 11. In question 11, it is asked that heat transfer between active particle and the fluidized bed is controlled by three mechanisms. Identify the wrong entry: radiation, gas convection, particle conduction. So answer is particle conduction is the wrong answer. So particle conducts with only the other particles. So main phenomena happening is radiation, gas convection and particle convection. However, because of the confusion this question is causing, I am going to remove this particular question and we will change the other questions number. The problems are pretty much straightforward problems where we are dealing with the and like yeah, two problems and two theory questions. So it is very easy. So in question 11 it is asked, choose the correct expression for radiative heat transfer rate on the wall surface. So what do you guys remember when we are saying radiative heat transfer? It is Stephen Boltzmann law. So there we are getting power of 4, if you remember, T to the power of 4. So just remember that. And option A, it is QR is equal to HR into AW into TP4 by T bed power 4. Or option B, it is QR is equal to HR AW TP minus T bed. TP is temperature of the particle and T bed is the bed temperature. Option C, it is QR is equal to HR into AW into TP square minus T bed square. So option D, it is none of the above. So I mentioned earlier itself that we are dealing with the radiative heat transfer, for which we need to get in mind the Stephen Boltzmann constant or Stephen Boltzmann law. There we would be using temperature to the power of 4. So on remembering that itself, we need to pick the answer as option A. QR is equal to HR into AW into TP power 4 minus T bed power 4, that is particle temperature to the power of 4 minus bed temperature to the power of 4. So I hope it is clear. Now we'll go to question 12. Yeah, we'll check the answer. It is option B. It is not option B. Okay, sorry. It is between particle and the bed. So it is Q is equal to HR into A into TP minus T bed. So I apologize for the mistake. So the answer is option D. So it is actually radiative heat transfer on the wall surface. Next question is another question, but here we are dealing with heat transfer coefficient and all. So right answer is option B. I really apologize for the mistake or the confusion I caused over here. So since we are dealing with the heat transfer, radiative heat transfer on the wall surface, we need to um, identify it, which is nothing but uh, in general, it is Tp minus T bed is equal to Qp into Hp into Sp. Sp is the surface area, that is pi dp square, and Q is the heat transfer. Change in the heat transfer happening inside the bed, and it is Qr is equal to HR into AW. Just a minute, I'll just be back. So yeah, the correct expression for radiative heat transfer is given by HR into AW into TP minus T bed, that is particle temperature minus bed temperature, because here we are not focusing on other aspects, we are just focusing on the heat transfer rate on the wall surface, which is nothing but heat transfer coefficient into surface area into temperature difference, that is TP minus T bed. I hope it is clear. Sorry for the confusion I caused earlier. Now we'll go to question 12. In question 12, asked that Stephen Boltzmann equation can be expressed as QR is equal to AW EBW into sigma into TB power 4 minus TW power 4, and option B, it is QR is equal to AW into EBW into sigma into TB square minus TW square. And option C, it is QR is equal to AW into EBW into sigma into TB minus TW, or none of the above. This is the question which I told before. So for this question only we are going to use TB power 4 minus TW power 4. So option A is the right answer for Stephen Boltzmann equation. I hope you remember. So it is TB power 4 minus T wall power 4. That is bed power, temperature of the bed minus temperature of the wall. Both are raised to the power of 4. So we'll go to question 13. In question 13, it is asked that determine the effective emissivity for the belt wall combination EBW, where EB is given as 0.9 and EW is given as 0.88. So effective emissivity of the bed is given as zero point 0.9, emissivity of the wall is given as 0.88. So what is the effective emissivity of bed and wall EBW, where EB and EW are given? So EBW option A it is 0.90, option B it is 0.52, option C it is 0.50, option D it is 0.80. So we'll solve this problem. Before that, if you have, yeah, take a minute and answer this. We'll solve it after a minute. Yeah. So yeah, now we'll solve this. Question 13 solution. So it is a very simple problem. This is because we are know the emissivity of the bed and emissivity of the wall separately. Just we need to identify the effective emissivity of the both. When E is given, which is 0.9, EW is given, which is 0.88, and EBW formula, EBW is equal to 1 divided by 1 by EB plus 1 divided by EW minus 1. So sorry, it is minus, not into, it is minus 1. So we are substituting all the known things in this particular equation. 1 by 0.9 plus 1 divided by 0.88 minus 1. So what are we getting? We are getting it as 0.816. EBW we are getting it as 0.816. If you want, just check. Okay, 1 divided by 0.9, it is 1.11, equal to 1 divided by 1.11, and then 1 divided by 0.88, 1.1363 plus 1.1363 minus 1. So minus 1 plus 1.1111. So it is 1 divided by 1.2474. Okay, it is 8016 actually. It is 8.8016. So we'll see what is the answer. So option D, 80 is the right answer. So option D is the right answer, 0.80. So I hope you all are clear in this question. What have we done in this particular problem? We are given the emissivity of the bed and the emissivity of the wall separately. So we need to find the effective emissivity EBW. So for the formula, it is 1 by 1 divided by epsilon EB plus 1 by epsilon EW minus 1. So in other aspects, it is 1 by EBW is equal to 1 by EB plus 1 by EW minus 1. So just taking the inverse, we are getting this. So on simply substituting all the known values in the equation, we are getting this answer. So we are going to the last question. In last question, it is given that calculate the radiative heat transfer coefficient HR given EB is equal to 0.89, EW is equal to 0.82 and TV is 300 degrees Celsius, TW is 150 degrees Celsius and S is 5.67 into 10 power minus 8 watt per meter square Kelvin power 4. Answer is option A actually. We will solve this particular problem. Question 4. Given, we will write the given data first. Whatever it is given, we will write. What do we need to find? To find, we haven't written anywhere and no one has informed me actually. Formula. Before that, we will see what else we can find from this. Okay, or else we can write formula also. I think this formula we have used somewhere actually. Yeah, this one. No, sorry, not that one. Actually, it is EBW into S into 4 minus T. Sorry. TW divided by bed minus T wall. So that's it. This is a formula. For this formula, what do we know? We need to know EBW. We need to know. For finding EBW, how did we do? We use the individual emissivities of the bed and the wall separately to find the effective emissivity EBW. So HR again for that we are using this, and first we'll calculate EBW is equal to So for EBW we'll be using 1 divided by 1 by 0.89 plus 1 divided by 0.82 minus 1. So what value are we getting? We are getting it as 0.7445. 7445. Or else we'll check again. One divided by 0.89. It is 1 divided by 1.1236 plus 1 divided by 0.82, it is 1.25 minus 1. So for this we are getting 1.25 plus 1.1236 minus 1. 1 divided by 1.3736 we are getting. So 1 divided by this 1.3736 0.7280. We are getting it as 0.72. Okay. Something is wrong. 1 divided by 0.89, 1.1236, 1 divided by 0.82, 1.21, not 2195 actually, 2195. So minus 1 plus 1.1236, 1.3431. 431. 1 divided by 1.3431, 0.7445. So we have calculated EBW. Now we need to go back and substitute the known thing in the this formula to find all the remaining unknowns. HR is equal to 0.7445 into S, it is 5.67 into 10 power minus 8, 5.67 into 10 power minus 8 into TB, it is 300 plus 273, 573 power 4 minus 150 plus 273, it is 323, 423 power 4 divided by 573 minus 423. So we are getting the answer as 573 power 4 minus 423 power 4 into 10 power minus 8 into 5.67 into 0.7445 divided by 150. 21.3273 we are getting. 21.3273. So this is how we calculate HR. It is watt per meter square Kelvin. So answer is watt by meter square Kelvin. That's how we calculate the heat transfer coefficient when we are dealing with the radiative heat transfer. So for that, how did we go about? Radiative heat transfer coefficient HR is calculated by using this formula. HR is equal to EBW into S into TB power 4 minus TW power 4 into divided by TB minus TW. So it is EBW we are calculating by using the individual emissivities 1 by EB minus 1 plus 1 by EW. Taking the reciprocal of this gives the EBW effective emissivity of the bed and the wall. And from this we are calculating it and we are substituting back in the HR equation. So HR, on substituting all these things, we are getting the value as this. So that's how this problem is done. So yeah, question 14 it is done. If you have any doubts, ask, or else we'll just quickly go through whatever we have seen in today's class and we'll close the session. Yeah. So yeah, we'll quickly go through once again. So in today's class we were dealing with heat transfer and the mass transfer and mostly design aspects of the problems. So the first question was about heat transfer characteristics in the fluidized bed reactor. So it is conduction, convection and radiation. So conduction is between particles and the particles wall. Convection is between from the gas to the particles or gas to the wall, or radiation is from particle to gas or the wall to gas. So that is the mechanism of heat transfer characteristics in a fluidized bed reactor. And after that it was about heat transfer coefficient, which increases with increasing thermal conductivity and increases with increasing density and increases with decreasing viscosity of the gas. So on top of that, we have calculated we have done one simple problem where we have calculated the Prandtl number, which is nothing but Cp mu by K. It is a simple substitution. And next we have calculated the Nusselt's particle Nusselt's number. It's similar to Sherwood's number. So we are using 2 plus 1.8 into Reynolds number power 0.5 into Prandtl number power 0.33. So if it is a Sherwood number, we would be using Schmidt number in place of Prandtl number. That is the only difference. Reynolds number, particle Reynolds number we are using. So it is rho v dp by mu, and Prandtl number it is Cp mu by K. Substituting all these gives the proper answer. And it was about calculating Nusselt's number of the particles, which is nothing but Hp dp by K. So because we are calculating heat transfer coefficient, Hp comes above and the contrasting features comes below because it is a dimensionless number. So that was a clue. And in question 6 we were dealing with the calculation of interfacial bubble area, which is nothing but 6 into epsilon g by dB. And another formula was based on that. Here the point to be noted is we are using gas liquid flow system where liquid hold up is given. So it is a direct substitution of question 6. And in question 8 it was about smaller bubbles have low rising velocity and also they have a higher gas hold up. The contrary statement is larger bubbles have low gas hold up. So both options are right. And Thiele modulus, which is nothing but reaction like it is between particle reaction constant or reaction rate constant by the particle mass transfer constant. So it is given by phi is equal to dp by 6 into kr double dash as by di power 1 by 2. And option 10 it is calculating of the slurry viscosity, where we are given the liquid viscosity and the solids hold up in a bubble column. So we have used this particular formula where slurry viscosity is equal to the liquid viscosity into 1 plus 2.5 into epsilon s plus 10.05 into epsilon s square plus 2.73 into 10 power minus 3 exponential of epsilon s. So substitution gives the proper answer, and radiative heat transfer is given by HR into AW into TP minus T bed. Here I have made a mistake, but please make sure you do not make that particular mistake, because it is asked about calculation of the radiative heat transfer coefficient, heat transfer rate. And the next particular question is about Stephen-Boltzmann equation, where we are using TP power 4 minus TW power 4. And in question 13 we are calculating effective emissivity of the bed wall combination, where emissivity of bed and wall are given. So we have used the formula 1 by epsilon b EBW is equal to 1 by EB plus 1 by EW minus 1. And the last we have calculated radiative heat transfer coefficient HR, which is nothing but EBW into S into TB power 4 minus TW power 4 by TB minus TW. So EBW first we calculated using the previous formula 1 by EB plus 1 by EW minus 1, and taking the whole reciprocal gives 1 by EBW. Substituting EBW in the HR equation, HR is equal to EBW into S into TB power 4 minus TW power 4 by TB minus TW gives the radiative heat transfer coefficient. So we have got the answer as 21.3273. So that's it for today's class. I hope you understood whatever things we have done in today's class. So that's all for today's class. This is for weeks 1 to 12. We have covered almost all the things in the class. All the necessary problems, everything. I hope this session helped you in some way in solving the assignment problems. If you have any doubts, you can always ask in the comments. So I'll be happy to answer whenever I see that. Or else if there is any doubts, you can post it in the forum also. So that's it for today's class. One more thing is, although like 12 week session is over, tomorrow we will be having one more session from 3 p.m. to 5 p.m. That is tomorrow, Saturday, 14th October. Where we will be giving a summary of whatever happened in this particular course, especially in the problem solving sessions, where we would be dealing fairly with all the concepts and any interesting problems if we have seen, that would be dealt in tomorrow's class. So please be available for tomorrow's class. It is between 3 p.m. and 5 p.m. So yeah, that's it for today. Generally we don't have the Saturday class, but tomorrow it is there. So that would be the last class. There you can come and join and give your feedback as well. Anything to be improved and anything you found useful in the class, or anything it was not good, all the feedbacks are accepted. Yeah, we'll meet again tomorrow. So since there is no one, we'll close the session. Yeah, thank you guys. We'll close the session now. Yeah.